if you want.
So, hello, everybody. Welcome back to the art seminar. Today we have Keefe Mitman tell us about what gravitational waves actually look like. It's great. I've never seen one. So,
Oh, and something already went wrong.
oh no. Okay. It's not sharing anymore.
No. Oh, is it not sharing on Zoom? Zoom messed up. Let's try this again.
Okay, there we go.
Okay. So look all right now? Okay. Yeah, so this talk today is going to be about what gravitational waves actually look like. I'm going to try to keep things light and playful. So if you guys have questions at any point, please just interrupt. Kind of the structure of this is we're kind of just going to work through a basic GR problem together that you could do as like an undergrad if you took GR as an undergrad. And then we'll delve into some more complicated things, but the first part is going to be pretty easy, I hope. So we're going to start by just kind of, jumping into this propaganda that's been presented for, I don't know, what, 7 years now since the first detection. And part of the problem is that all the propaganda is from the numerical side. So really, it's just us, the numerical relativists, have been lying to everybody. And pretty much just convincing the whole gravitational wave community that waveforms look this certain way, when in fact they look completely different. And we're going to find out the truth for ourselves. So we're going to delve into some calculations and really make sure we know what's going on and kind of realize where the numerical relativists went wrong. And so that'll be kind of the first half of the talk, which should be fun. And then the second half is going to be a lot more involved, but I'll try to keep it simple enough so people can follow along. Okay, so let's just jump into this. So this is a numerical simulation of a GW150914 like binary. So it corresponds to the first signal that LIGO saw. And here on the vertical axis, I'm plotting the plus polarization of the strain. And then on the x-axis, it's just time. And so the way we kind of run this simulation is we evolve our black holes in what's called a Cauchy evolution. And then we extract the waveform to asymptotic infinity using this procedure called extrapolation, which I'll touch on a little bit later. And so this is pretty consistent with what's typically shown in LIGO plots. So here's a common one you see on LIGO's webpage where they kind of have the numerical signal here, and it looks pretty similar to this one. They're a little bit different because the one I'm showing is at a different sky angle, but it's just to kind of highlight something later on. And so as you may guess, this is completely wrong. It's an absolute lie. So this is not at all what gravitational waves look like. If someone ever shows you a gravitational wave like this, you should be, Keefe told me that's not what they look like. Why are you showing a wrong gravitational wave? It should really be, whenever somebody gives an astronomy talk and somebody asks about magnetic fields, whenever somebody gives a talk and shows a gravitational wave, you should always ask, is that really what they look like? Because they don't look like this, they look like this. And so what's really going on is that whenever you have a gravitational wave, not only is there this, oscillatory signal that LIGO is going to detect, but there's also this permanent offset, which you can kind of think of this evolution of the average value of the strain. And so the name given to this average offset, which I've highlighted in red, is called the gravitational memory effect. And so essentially what it corresponds to is that whenever a gravitational wave passes through LIGO, you don't only get the different arms of the detector oscillating back and forth, but they'll actually end up permanently displaced if LIGO were truly free falling, which it is. So there's a bit more complication in terms of practice, but if you and I were like floating in outer space and we were free falling, then we would experience this permanent displacement due to this memory effect. Okay, so this is a full numerical simulation. So this is pretty hard to do. This takes 10 years. You don't have 10 years in this hour-long talk to run, to write code and run such a simulation. So instead, let's just try to do a simple problem. So I think Saul actually gave me this problem in his GR class, which maybe some of you have taken. But the problem is the following. So we have 2 point masses, which are just orbiting each other. They are separated from the center of mass by radius r1 and r2 in the xy plane, and they're orbiting with some angular velocity omega. And the task that we're given is to use the quadrupole formula, right, which comes from first order perturbation theory, to compute the gravitational wave strain that's emitted by this binary system. Okay, pretty straightforward. But the thing I want to highlight is really this is going to be a first order perturbation theory problem. And we're going to take this a step further, which is usually not done in GR. But this is where we're going to start. So the kind of way you start this problem, you set all of your constants equal to 1, so you don't have to worry about them. And then the quadruple formula says that the trace reverse metric perturbation, this h bar, is equal to 2 over r times the second time derivative of this quadruple moment tensor, where this quadruple moment tensor is just this integral of the mass density and these extra radial dependence. And so for our binary system, we can treat the mass density as just these delta functions kind of located on these point masses. That's just weighted by the point mass itself. Okay, so if you just take this mass density and you plug it into the integral and you work through this integral with all the delta functions, which isn't too bad, and then you convert to the transverse traceless gauge and use the quadruple formula to extract the strain, what you obtain is the following. So you get that the plus polarization has this factor of 4 over r times the total mass of the system times the reduced mass nu times this parameter x, which is called the post-Newtonian parameter. It essentially just is related to the angular velocity of the binary. Then you have this different angular dependence, depending on whether or not you're looking at the plus polarization or the cross polarization. And so that's pretty cool, right? Just from some simple math, you can work out what the gravitational wave emitted by some binary is and do some pretty rough estimates on how likely it is to observe such a thing. But as numerical relativists and in the analytical community, usually we don't like to write the strain in terms of actual functions on the two-sphere. Usually we just like to use some kind of basis. And so since gravity corresponds to this spin-2 field, the gravitational field, the way we decompose the strain in terms of some functional basis is we use spin weight -2 spherical harmonics, which are these things here. So they're essentially just your spherical harmonics, but then you add on this extra thing called spin weight, which just kind of changes their dependence a little bit. And so if we take those previous equations and we just rewrite these angles as in terms of spin weighted spherical harmonics, what you get is you have kind of the same prefactor, now some extra term to account for the weight on these spin weighted spherical harmonics. And you just get that you have an excitation in the 2+2 mode and the 2-2 mode, which should make sense because the quadrupole corresponds to L equals 2. And if you're going to excite an L equals 2 mode, you should probably have your M equal to that L, or equal to the absolute value of M equal to L. And so that's exactly what you have here. And then you just have your time dependence, which goes as e to the minus im omega t, where here M is just going to be 2. And congratulations, you've just derived the 0th order PN result. And so in the analytical community, people are really obsessed with deriving PN results because they essentially tell you what your waveform should look like in the early in spiral of your binary system. And then this is almost true. You've actually almost derived the 0th order PN result. The issue here is your binary isn't coalescing at this point because it's just orbiting with some constant angular velocity. So if we want to fix this, we should actually figure out what this time dependence of omega is. And to do that, we just have to account for the energy loss of the system. And so this is also usually just kind of a basic problem in a GR class, but we'll go ahead and work through it. So the way you do this is you know that the change in the energy of your system as a function of time is going to be balanced by some flux, which corresponds to the energy carried by these gravitational waves. And so the energy of your system is just going to be the binding energy according to the masses of your binary objects. And then your flux corresponds to essentially now the 3rd time derivative of your quadruple moment tensor. And so if you work this out, just like in the previous problem, you get this. And so you can use these two formulas in the first one to kind of come up with some ODE for R and omega. And if you remove the dr dt terms and just solve for the d omega dt terms, what you obtain is the following. And so with this, we can kind of figure out what the phase of our binary system is going to be, because the phase is just going to be the time integral of omega. So if you solve this ODE for omega and then integrate it with respect to time, you'll get the phase of your binary, which is what we want to replace that omega t term with. And so if you do that, if you solve this ODE and then just integrate it, what you get is that the phase of your binary to leading order goes as this PN parameter to the -5/2 power. And then the other thing you can do is you can actually just actually, I guess first, yeah, so just plug this in. Now we have the same equation as before, but you replace the omega t with this psi of x. And then the other thing that's important, which we'll need for later, is that while this is an ODE for omega, since omega is directly related to this parameter x, we can just also get an ODE for x, which is the following. And so this is kind of the most important stuff. We have the phase of our binary system, which now is changing as a function of time. And we have the time dependence of this x parameter. Okay. But so far, right, this has all been first order perturbation theory. So we really haven't done anything interesting. I mean, we figured out what the gravitational wave is, and we figured out how the binary is going to coalesce, but this is all still just linear GR. So let's try to do something nonlinear. And so this is kind of the new thing. So this usually isn't done in GR because this is a little bit more complicated. But one thing you can do is you can consider something known as the Weyl tensor. So the Weyl tensor is similar to the Riemann tensor. You can kind of think of it as the trace-free Riemann tensor, because the Weyl scalar really measures the change in a shape of an object along some geodesic when it's being tidally deformed, rather than the change in the volume, which is what the Riemann tensor measures. And so what's nice about this Weyl tensor is that if you work in the Newman-Penrose formalism with spinors, then you obtain this nice set of equations, which is just equivalent to the usual Bianchi identities that you have for the Riemann tensor. And so what these Bianchi identities state is that you have these 5 different Weyl scalars. It says that the 4th Weyl scalar is equal to essentially the second time derivative of the shear, which you should just think of as the strain. Psi 3 is just the news. Psi 2 has this weird imaginary law. And then there's this other one where the derivative of psi 2 is related to the news and this product between the shear and the second time derivative. And so this one is actually the one we want to focus on. And the reason why is that if we integrate this with respect to time, then rearrange it, what we obtain is we obtain this equation for the shear, which is now expressed in terms of the second Weyl scalar psi 2, which you can think of like the mass multiple moment. This weird kind of nonlinear looking term, and this other weird nonlinear looking term. And so in our previous calculation, where we did that PN calculation, effectively what we did is we just computed psi 2 to leading PN order. And so when we did that, we got these 2 harmonics, which are the dominant harmonics of the string. This second term here, this is kind of just this weird thing that nobody understands, but it only contributes at higher PN order. So since we're just doing first order PN theory, we don't really have to worry about it. But this last term is interesting. Something special about this last term. And part of the reason why is because we have 2 time derivatives here, this may actually contribute at this 0th PN order. And so the way you can see that is through the following. So if we go ahead and try to compute what the LM modes of this integral term are, the way you do this is the following. So you just say, I want to know the LM components of this term. So you integrate it against the spherical harmonic of those LM modes, which is this spherical harmonic showing up here. And to do so, you have to really sum over all the modes, which are defining your 2 different shear objects in this integral product. And so when you work everything out, you have the sum over all these modes of these 2 different shears. You get this angular integral over the angular functions, and you get this time integral, which was the time integral that was there in the first place. But now it's just a time integral over the individual modes. And so this integral over the sphere, this is really easy to compute. You just write these spin-weighted spherical harmonics in terms of Wigner D matrices, and then Wigner D matrices have nice integral properties, and so this just spits out some weird number. But the important thing to note is that one of the properties you discover is that when expressing these in terms of the Wigner D matrices, it actually requires that the M of the M you're extracting is equal to negative M1 plus M2. So that means if we have a 2,2 and a 2 minus 2 mode from our original PN calculation, the only M modes we can excite are is the M equals 4 mode, so 4, 4. M equals 0 mode, so like 2, 0, 3, 0, 4, 0, or the 4 minus 4 mode. Okay, so those are the only things we're going to be looking at. This time integral, since our PN waveform is written in terms of this PN parameter x, really what we should do is we should change this integral to be an integral over x, change these time derivatives to be or derivatives with respect to x, and use the phase and x dot information that we extracted before. So specifically, we can convert the time derivatives from time derivatives to derivatives with respect to x, which for each time derivative brings down an x dot. So we'll get two x dots from these, and then changing du to dx gives you an x dot inverse. So you end up with just one factor of x dot, which is here. The primes denote derivatives with respect to x. And so then if you plug in these h primes, the term that's going to be the leading PN contribution is when you pull down this time derivative or this x derivative of the phase twice. And so if we kind of just do some counting, I'll kind of refresh your memory about what the order of these things are. So x dot goes as x to the 5. With the x squared, it'll be x to the 7. When we take a time derivative or an x derivative of psi, it'll give us x to the minus 7/2. But since we have two of them, it'll be x to the minus 7. So here we had 7, here we had minus 7. That gives us 0. So when we integrate, we get something appearing at order x, which is the same order as the stuff we had earlier. And so the only way you can bring down these psi primes is actually when your M1 and M2 in this sum produce an M of 0. So the 4-4 harmonics appear at higher PN order. It's only the 2-0 mode that gets excited here. So if we kind of do everything formally, like I just said, we get one spherical harmonic mode that's excited due to this nonlinear interaction, and it's this 2-0 mode. And so it looks like this. It has kind of the same prefactor as the 2-2 mode, still linear in x, and there's just this extra 5/14 square root of 6. And so this, if you kind of look at it, it's non-oscillatory, it's monotonic, it's gravitational memory. Yay! All right. Cool. So just from kind of basic GR and a little bit of understanding of where nonlinearities arise in the shear, you can kind of really easily derive this leading order PN interaction that produces this gravitational memory effect. Okay, so with that, we can kind of delve into what things look like numerically. And so in numerics, right, we always take our strain and we decompose it in terms of these spin-weighted spherical harmonics. So the first thing I'd like to do is kind of just show what these kind of look like. So here, this is the waveform from an equal mass non-spinning system. You can kind of ignore what all these terms are in the legend. We'll come back to these. But the main thing to note is here, the 2-2 mode is really the dominant mode. It's the dominant mode in PN, and it also turns out to be the dominant mode in numeric simulations. And kind of as you expect, right, there's some in-spiral ringing, then there's a merger, and then some kind of ring down, which is Blackwell perturbation theory. If you look at the 2-0 from your numerical simulations, if you do them right, we'll get into what people are doing wrong later, but if you do it right, what you get is this. So again, you have some kind of monotonic, non-oscillatory piece during in-spiral. It really ramps up during merger, and then there's some oscillations on top of it that eventually decay away to some final value. And so typically, right, people, when they first discovered the memory effect analytically, they thought it would be really small, but for your typical binary, it's actually going to be about 25% the maximum value of your strain. So it's a really prominent effect. Okay, and so this should kind of explain, right, when we have this 2-2 mode and this 2-0 mode, that's why you get a signal like this. So you have oscillations from 2-2 and a permanent offset from 2-0. Okay. Any questions about that derivation? Easy peasy. Do it in your sleep, right? Unbelievable that people were doing it wrong this entire time. And it's like something you could do as an undergrad. Kind of embarrassing. So that's memory. But it turns out memory is actually a lot more insightful and interesting than that. And this is where things get a little bit more abstract, but I'll try to explain things nicely. So one thing people learned about asymptotics and gravitational radiation is that if you consider gravitational radiation as existing at kind of the edge of the universe at infinity, then it's nice to understand what the symmetries that radiation is going to obey. And so these people named Bondi, Vanderburg, Metzner, and Sachs in the 1960s, they set out to figure out what this asymptotic symmetry group is for general relativity. And they thought they would just get the Poincare group, right? If you have empty space-time, if you translate it, it looks the same. If you rotate it, it looks the same. If you boost it, it looks the same. And so they thought they would get the same thing at infinity. And so the way they did this is they came up with a metric that describes asymptotic radiation called the Bondi-Sachs metric. And what they did, this was the hard way, but they're physicists, so they always do things the hard way. They essentially came up with some arbitrary class of vector fields and looked at the vector fields which satisfied Killing's equation. So they looked at the vector fields whose Lie derivative on the metric yielded 0 with respect to fallout conditions that they imposed. And so what they found is they found this vector field, which essentially has this alpha term, which is some function on the 2-sphere, and these terms related to this y vector, which is also a function on the 2-sphere. And so if you look at kind of the lower order harmonics, so the y vector can only have harmonics of L equals 1 or higher. And so the L equals 1 harmonics, these are just boosts and rotations. And for this alpha term, since this is appearing on this partial u, if you look at the lower order harmonics, so L equals 0 is just a time translation, and L equals 1 is just a space time, or it's just a space translation. But because this can be some arbitrary function on the 2-sphere, it means you're also allowed to consider transformations with higher harmonics. And so what they discovered is that you actually have this infinite number of symmetries, which they called super translations. This is really complicated though. There's a much easier way to think about it. So instead, just imagine you have some collection of observers on a 2-sphere, and say they're witnessing some kind of event. It could be like a binary. So when they're at some finite radius from this binary, they could, with an understanding of like where they're located relative to each other, just kind of synchronize their clocks and change their clocks so that they all receive the same information from this binary at the same time, even though they're kind of at different locations. But if you push these observers to asymptotic infinity, then they're now disconnected from each other. So you can freely time translate without changing any of the observable physics. And so these super translations are just direction-dependent time translations, which is a little weird, but that's just what they are. It's essentially when you have these observers at infinite points on the 2-sphere, you can just change their clocks freely, and it's not going to change anything about what they're seeing. Okay, so that's kind of where these super translations arise. And what's really interesting about additional symmetries is from Noether's theorem, we know that whenever you have a symmetry of your system, there's going to be a conserved charge or a charge that's balanced by some kind of flux. Okay, so to compute what these charges are, these people, so Dre did it first, but then Wald and Zupas kind of did it better. They figured out that if you just take your Bondi-Sachs metric, which is the metric that describes asymptotic radiation, you can kind of study how these different symmetries transform the metric to understand what parts of the metric can be considered charges that correspond to these symmetries. And so what they found is they found this thing called the Bondi mass aspect, which corresponds to these super translation symmetries. And they found this Lorentz aspect, which corresponds to Lorentz transformations. And so there's many different choices you can make for what these charges are, but this is the only choice that makes it so that there's no fluxes in Minkowski space, which is something you want. If your space is just empty, you don't want there to be random fluxes in certain places. And this is a little bit weird, but essentially it corresponds to your momentum being real. It turns out with these super translations, which extend translations, you actually have something called a super momentum. And so this just makes it so that your super momentum is real. But I wouldn't worry about that too much. Okay, so if you identify these charges and you look for them in the Bondi-Sachs metric, then you obtain the following balance laws, right? So this is just the usual balance law in the sense that if I have a change in mass, it has to be balanced by, an energy flux, for example. And so actually this first law is exactly that. So this term on the left, this only has contributions when you're looking at harmonics with L greater than or equal to 2. If you look at the L equals 0 component of this equation, that's just the mass energy conservation law. If you look at the L equals 1 harmonic, that's just the momentum flux conservation law. The higher harmonics are what we call these super translation balance laws. Similarly, if you look at this imaginary part, this kind of corresponds to the angular functions on your two-sphere. So the L equal 1 harmonics of this correspond to conservation of angular momentum. Okay, but what's interesting is this says not only do you have some charge that's balanced by a flux, but there's also some weird non-zero contribution that's proportional to your strain. So now we don't just have a charge and a flux in our balance laws. We have a charge, a flux, and some kind of strain thing. Okay, but this is kind of a really nice way to think about gravitational radiation because it tells you that your shear is really just some charge plus some flux. Same thing for the imaginary part. Your imaginary part of your shear is just equal to some charge plus some flux. And so this E here, this is just the energy flux of your system. And this script J is just the angular momentum flux. M you can think of as your mass, and N you can think of as your angular momentum. And so this is what I was showing earlier, where here I'm showing the 2-2 mode of the gravitational wave from a numerical simulation. So gray is the total wave that we measure. And you can see that the 2-2 mode is entirely sourced by this mass charge, right? All the other terms are pretty much 0. And that's not too surprising, right? Because this mass charge is directly proportional to that second bioscalar. So earlier when I said, we did this PN calculation and we really just calculated the PN part of psi 2, that's essentially what this is showing, is that the dominant contribution to gravitational radiation is really just from that multipole moment fluctuation, which is exactly this mass charge. When we have a mode that has the same, so if your L is even and your M is also even, that's called an electric parity mode. Isaac, did you have a question? Okay. And if your L is even and your M is odd, that's called magnetic parity. And so if we want to look for something that's sourced by, say, the Lorentz charge, we just have to look at a harmonic with magnetic parity, which would be 2-1. And so if you look at 2-1, you kind of see a similar thing where the 2-1 mode is sourced almost entirely by this Lorentz charge. There's some other contributions from the flux here, but it's pretty much all sourced by this Lorentz charge. Okay. The other interesting thing about these balance laws, though, is instead of thinking of them as a function of time, you can think of them as a net change over all times. And so if you think about this equation as a net change over all times, then you're looking at a net change in the strain. And the net change in the strain is exactly this memory effect. And so it turns out that from these balance laws, you can actually identify many different types of memory. So here I've just kind of written these balance laws as a net change over time, where this delta means you take the value at plus infinity and you subtract the value at minus infinity. And for the imaginary part, you actually have to integrate it. And so what you learn is that kind of the memory I was showing you earlier is called displacement memory because it corresponds to observers being displaced. And so there's essentially two ways this can arise. One is from this energy flux, which is that PN calculation we did. And the other way is from a change in your body mass aspect. And so people actually discovered this memory first. They called it linear. The more modern nomenclature is called it ordinary. And then some other people found this other type, which they called nonlinear or Christodoulou, but the more modern terminology is null. And so kind of the easiest way to identify what systems produce these types of memories. So obviously from our PN calculation, if you have a binary, so any kind of system that is kind of bound, you're going to produce this null displacement memory. Whereas if you have like a hyperbolic system that comes in and scatters, then that's going to produce this ordinary memory. So LIGO is going to see null memory because it sees binaries. But if it saw some like really massive, like supermassive black hole scattering, it may be able to pick up this ordinary memory. The other type of memory that's a little bit weird is this memory associated with the Lorentz aspect. And so what this corresponds to is actually it's a memory effect in the time integral of your strain. And so kind of the easiest way to think about that is for displacement memory, where it's this kind of physical displacement that you observe, this memory in the Lorentz terms, one kind of way you could observe it is if you have the Large Hadron Collider and you have your particle beams that are counter-orbiting, the gravitational wave passed through the LHC while they were doing one of their runs. You would actually see each of those beams experience a different time shift. So it's kind of more, it's easier to think about it as a net change in the relative time experience rather than a net change in the relative space experience. Yeah, okay, so kind of what these look like in the waveform. I already showed this is what the displacement memory looks like. It's entirely sourced by this energy flux. These oscillations at the peak of the strain, these just correspond to your permanent black hole ringing. So these are what you would model with quasi-normal modes. And then the spin memory, this kind of looks like a bump function. So here you can see that the imaginary part of the 3-0 mode looks like a bump. And so if you integrate a bump with respect to time, then you get kind of like a step function. So this is where the spin memory shows up in the strain. But if you look at the vertical axis right here, it's like 10 to the -3. Here was 10 to the -1. So spin memory, which is what this is really, really hard to see. And we'll probably not see it for a long time, but still cool. Okay, so part of why we weren't seeing any of this stuff before, right? Why was there this big lie from the numerical community? You can kind of just think of it as like a lapse in judgment, right? People put all of this work into simulating these binaries and solving Einstein's equations on some finite region of space-time where these binary black holes are orbiting. But once that was done and they had the metric at some finite radius, instead of connecting that radius to infinity and solving along that kind of extended part of space-time, they just said, okay, let's take our waveform at the world tube and let's fit to it with polynomials in 1/r. And the coefficient of the 1/r piece, that's going to be what the waveform at infinity will look like, because the 1/r squared, 1/r cubed, those all just die off. So they didn't actually solve Einstein's equations from the world tube to infinity. They kind of just estimated what it would look like. And so that's what extrapolation is called. So you kind of run your simulation in front of this red line. You get your metric at this red line, or I guess, sorry, you run your simulation in front of the blue line. You get your metric at a series of different radii. You fit the metric at those different radii with polynomials in 1/r. And then the strain is just going to be the 1/r part. Yeah, but obviously, right, wrong. Ended up just, totally ruining the gravitational wave community. Because now everyone thinks that gravitational waves decay to 0. They don't. A better way to do it is to just actually solve Einstein equations on the region connecting your world tube to asymptotic infinity. And so the way you do that is you run what's called Cauchy-characteristic extraction. And so you essentially take the same metric you get from your Cauchy evolution, but now you just build a numerical code that essentially creates a null hypersurface that connects your world tube to asymptotic infinity. And then you just evolve that forward in time where your inner boundary conditions are set by the data on your world tube and your outer boundary conditions are set by the boundary conditions you would have at infinity, namely that nothing comes in from infinity. And so if you do that, right, you get waveforms with memory. So CCE is kind of the future of numerical relativity. It's really just been a thing in the past 2 years, but already we know how to work with CCE waveforms. We know how to run it really fast. We're building surrogates for LIGO, so those should be out in like a month. And then hopefully, we can actually start doing some analyses on how detectable memory is going to be. There's actually a way to improve this further, which is kind of simple, and I'll just mention it briefly. It's called Cauchy-characteristic matching. So instead of kind of evolving the black holes and then going back and evolving these hypersurfaces, you just do it all at once. So you evolve this part, and then you evolve this. And if you get anything that bounces back off like the curvature of spacetime, you feed it back into your Cauchy evolution, and then here, and like you just keep going back and forth. And so there you might get some more interesting nonlinear effects. Okay, but that's kind of the main points on memory that I just wanted to mention. So just to kind of highlight what's going to be exciting for the future. With CCE and kind of these future NR codes, we can build much more correct numerical waveforms. Hopefully we can then, detect memory effects. It turns out that when we have this binary merger and you end up with some remnant, because there's memory, your black holes are actually super translated. So that might be some interesting observable thing. Like if you have the Einstein telescope, it might look out and be like, oh, that black hole doesn't look like a circle, it looks like an oval. It means it's super translated. So we might detect super translated black holes. Just like how memory is kind of this result of symmetries at asymptotic infinity, it turns out that the horizon of a black hole looks a lot like asymptotic infinity. So it turns out the horizon of the black hole actually generates its own type of memory effect, which is called black hole memory. So we might be able to see that. It helps us understand asymptotic symmetries more. So I mentioned those super translations. There's also these proposals that you might be able to promote rotations and boosts to be super rotations and super boosts. There's actually even more symmetries beyond that people propose. So hopefully we can figure out which of those are actually real. People have actually solved the black hole information paradox using super translations in memory. So that's pretty interesting. It actually makes quantum gravity a lot harder because now you don't have a well-defined Fock space. But then it actually also makes quantum gravity a lot easier because it tells you that any black hole will actually decohere any quantum state that you have, which is a paper that just came out like a month ago, which is pretty crazy. Turns out all these balance laws I was talking about are really soft theorems in quantum gravity, which correspond to essentially whenever you have gravitational radiation that's being emitted, it actually emits an infinite number of what are called soft gravitons, which are just like gravitons that asymptote to having no energy. And there's probably a lot more, but since you guys probably want to get home, I'll kind of just leave it at that. And to wrap up, I'll just say, may this talk, forever permeate your gravitational memory. Thanks.
Last things?
Yeah.
So I guess I'm still a little bit confused why extrapolation is unable to find 1 over R. Like, does this effect not fall off like 1 over R in the?
It does. But so part of the problem, so like no one really knows why, because like no grad student is going to want to like dig into the code and figure out what's wrong, right? Like that's just like, nobody likes just figuring out what's wrong with something. The idea that we kind of have is, right, memory is this clearly nonlinear effect. And moreover, it's not nonlinear in the strong regime, it's nonlinear in the weak regime. So it's nonlinear as your wave is propagating. And because extrapolation is just kind of extending the interior region, which really just captures strong interactions, by not capturing these nonlinearities in the weak regime, because it's not actually solving Einstein's equations, it doesn't actually get memory. But like part of why we think that is when we run these Cauchy evolutions, we found that the remnant is still super translated, which means the Cauchy evolution is working in terms of these extra symmetries. It's just that the waveform itself is not correct. So there's kind of this breakdown between the strong regime and the weak regime in our numerical simulations.
Like stitched correctly with
Yeah, exactly. And so we know that like CCE has problems. Like if you look at the violation of the Bianchi identities, the psi 0 Bianchi identity, which corresponds to incoming radiation, so it'd be radiation that should go back into your kind of strong regime, that Bianchi identity looks really, really bad. But if you run CCM, then it looks a lot better. So it's clear that CCE is pretty good, but we're going to do a lot better with CCM. So hopefully we can get that off the ground. Question? Yeah.
Yeah. So in terms of like, I guess like LIGO, like I know you can like, it's expected you like stack event space so you can find some SNR loss due to memory that you didn't model.
Mm-hmm.
But talking about like actually including it in the waveforms, given that LIGO isn't sensitive to these like really low frequencies at all, would you expect to find some sort of difference in the mismatches when you actually use CCE or waveform that includes memory?
Yeah, so this is something we're excited to look into because at one point they had done kind of a study where they looked at mismatches where they're using a surrogate that didn't have higher harmonics and a surrogate where they did have higher harmonics. And even though these higher harmonics shouldn't really be detectable by LIGO, they saw really big differences in terms of parameter estimation. So even though these things may not be directly observable, it could be the same thing that memory might still really impact these results. In terms of the low frequency, right? So I guess I'll just go here. Right, so a lot of people usually think of memory as a zero frequency effect because it corresponds to this net offset. But you can see, right, the memory that contributes to this waveform isn't just a step function, it's kind of a smoothed out step function. So if if there were a really, really loud event, maybe in the next LIGO run, you could technically see memory just like right there. I think what would happen is your waveform would it would have its oscillations and it would go up, and then it would kind of just get forced right back down based on the mirrors being stationary, or not stationary, but not truly free falling. So yeah, it probably is going to make a difference, but it's hard to tell how big of a difference it's going to make. But hopefully we'll be able to run some of those tests and figure that out.
Understand the detector response and then.
So that's something like Katerina was really interested in detector response, because like I have no idea how LIGO works.
That's what I was over too, but like surrogate, if you're making like a surrogate model, it has to be able to, it's not gonna be able to just like a standard detector response, right?
But I guess like probably the details of the detect, like the control system will also matter at that point.
What if field force from the memory have to like actuate it?
Yeah. Because I guess like the design of LIGO is also a lie in a way, because the arms can't stretch really. They're
Exactly, yeah.
Say in the configuration that. So I have no idea why.
Yeah, so I mean, that's why I was thinking like you're going to see the frequency associated with the memory effect, but you're definitely not going to like, walk down your arm tube and be like, hey, like that's longer than it was last time. Yeah, so. Yeah, it's probably going to be like, that's what we're hoping, is that by kind of showing the world that this is what gravitational waves look like, people will start thinking about these problems, and LIGO will start thinking about, how are we actually going to affect this result when we see something.
Do you know how that's like handled, like with the current surrogate that you're developing, like the detector response?
I mean, so the surrogate, right, it's just going to be an interpolation between the waveforms themselves, right?
Right.
Yeah, so then it's
someone, I assume there was something like LIGO to work with the detector response.
Right now, I'm just trying to get the surrogate.
Yeah,
Yeah, but I was going to hit up Isaac and be like, hey, help me out. Yeah, so that should be soon. We like just pretty much got it working this past week. So.
Any other questions? Let's take our speaker again. The next presentation is in 2 weeks. It will be by Isabel. Thanks, everyone.